just a few things. So last night I got a few emails about my math lab being down, so I figured I'd just push back that homework to tonight. So now you have two things. If you haven't done so already, now you have two things due tonight, so please make sure you get those done. And you may also notice that now the Unit 1 assessment is now available for you to take at any time. I did send out an update. It's 60 minutes and not 70 minutes, so I wanted to give you all a heads up. It's still 13 questions. Still don't think you might, I still don't think you would need that much time. Or I looked at some of the questions. They didn't seem like they would need a significant amount of time. But other than that, yeah, Unit 1 assessment, you could take it any time from now until September 11th at 6 p.m. So just make sure you're familiar with these due dates. And today we're going to be talking about linear equations and inequalities. And so let's go ahead and do that. Also, just keep in mind the workbook pages that I assigned are due Friday as well. I mentioned those in an email. So that definitely means you need to have the workbook by now. So go ahead and get those turned in by Friday as well. So those are the next few due dates. I went ahead and updated the notes as well online. So I have all the notes in here from now until the midterm. So if you want to go ahead and print all of those out, I have everything in here will cover up to the midterm. So just a heads up as well. So, okay, let's go ahead and get started. So we're gonna start off talking about linear equations and inequalities, which may seem like a fairly familiar thing. Primarily what this section breaks down to is practicing the concepts of, well, how do we take these complicated expressions and simplify them down using, well, I guess the technique of, say, combining like terms, or using the distribution method, or the FOIL process, all of these things that we've already done before, but now we're just going to be working on them. The main thing we're going to be looking at is applying an LCD, because there's some problems in this section that are, well, a lot of them evolve around fractions. And I do want to talk about the strategy that I use for dealing with fractions, and that's going to be the primarily the problem set that I look at. I did give a note that if you have any expressions like this, x plus 3 squared, it's not x squared plus 3 squared, but instead I wrote down right below it how you have to handle that via distribution. Or via FOIL, rather. So just a heads up with that. You might find a lot of stuff in here to be review, and if so, this section might not be too bad. But primarily what I wanted to look at is the least common denominator. And the least common denominator, well, it's some multiples, the lowest common multiple of all the denominators. That's it. The lowest or the least common multiple of all the denominators. And we'll do a bunch of problems like this to really practice how to find this, but this is a strategy we will be using for the remainder of the semester. This idea of a least common denominator. So defining it is one thing, applying it is another. So let's go ahead and do that. So we look at example 1 here. And normally my thought process is anytime I see a fraction, I'm going to think LCD. This is going to be something I'll be pretty consistent with for the remainder of the semester. So if you have an equation you're trying to solve and there's a fraction, I'm I'm going to mention the least common denominator first. And so it might already be something you're familiar with. I see a fraction. I think the least common denominator. Well, perhaps let's take a step back. I think we all know what a denominator is by now. So the denominators in this problem are 3 and 4, obviously. So the least common denominator is going to be the smallest number or expression that 3 would divide into and 4 would divide into. So if you were to choose 3 for the denominator, and obviously 4 doesn't go into 3, you chose 4 for the denominator, or the least common denominator, 3 does not go into 4. Say go into, I mean, what does the ratio look like? What would 4 divided by 3 look like? So you could try to pick 6. 3 goes into 6 because 6 divided by 3 is a whole number, it's 2. But 4 does not go into 6 because 6 divided by 4 is not a whole number. So that's, when I say go into, I just mean it's a division. So here the least common denominator ends up being 12. So let's think about it. 12 is the least common denominator because 12 divided by every denominator that we have is a whole number. 12 divided by 3 is 4. 12 divided by 4 is 3. And that is the thought process we are going to use. The least common denominator is the least multiple of all the denominators, or in other words, it's the smallest number or expression that all the denominators go into. So the question is, all right, we have the least common denominator. So what? Well, now what we do, so I write it furthermore in this description up here. We find the LCD for any equation involving a fraction. Once the LCD is found, you multiply it to every term in the equation. So the LCD is 12. Well, then we multiply everything by 12, every term. So that first fraction, the x plus 4 over 3, gets multiplied by 12. The x plus 1 over 4, that gets multiplied by 12. The 3 at the end gets multiplied by 12. Everything gets multiplied by the least common denominator, whether it has a fraction or not, just everything. That's why I have every term italicized above. It's legitimately every term. Now I want to add a different color here. So I can emphasize how the least common denominator interacts with the fraction. So when you apply a least common denominator, after you apply it, all of your fractions will be gone. If your fractions are not gone after you apply the least common denominator, then you did not apply it correctly. That is the point of it. You apply least common denominator and all of your fractions will be gone from the problem. So for this first fraction, the 3 and the 12 will interact as 12 divided by 3. Which is 4. So if anything, that first term will now become 4 times x plus 4. And the x plus 4 is because that numerator stays. And so for the next fraction, the 4 and the 12 come together. And since the 12 is in the numerator and the 4 is in the denominator, then we look at 12 divided by 4. Which is 3. So now it's plus 3 with the x plus 1 that follows. And then finally, we have 3 times 12. It's just 36. And notice all of the fractions are now gone, which is the point of the least common denominator. Now we can simplify this problem much easier, much more easily. From here, it's just a matter of distribution. And combining like terms. And so we get that x is 17 over 7. So this is the general process, and we're going to be going over a few more of these. This is the idea. Does anyone have any questions so far? Or if you do, I suggest you might want to wait until after problem 2 here. So let's go ahead and look at problem 2. We're going to do the same exact thing. So you look at problem 2 and it says solve. The first thing I think of is, well, I see 2 denominators. Three and 9. So that's all the numbers or expressions in a denominator. The least common denominator is what's the smallest number that both 3 and 9 go into. And it seems to be 9. 3 goes into 9, because 9 divided by 3 is 3. And 9 goes into 9, because 9 divided by 9 is 1. So your least common denominator could possibly be one of the denominators. That's perfectly okay. But we choose this on purpose because we want this cancellation to happen, where the fractions will guarantee to cancel out. That's why we pick the LCD with this divisibility criteria. But once we pick the correct LCD, we multiply it to every term, whether it has a fraction or not. And when I say term, I mean things separated by a plus or minus sign. Expressions separated by a plus or minus. That would be a term. So over here on the left, we have 9 divided by 3. We have the LCD interact with the fraction to guarantee the cancellation. And so 9 divided by 3 is, of course, 3. So if anything, we could start writing this out. That's 3 with an x, because there is still an x there that did not get canceled out. It does not disappear. It lingers and it follows through. The next one, we have negative 5 times 9, which is negative 45, or minus 45. And then for the final one, again, the least common denominator interacts with the denominator. So 9 divided by 9 is just 1. We still have a 4x over here. So technically it would be 4x times 1. But anything times 1 is just itself. And by subtracting 3x on both sides, we can combine like terms. And x is now solved for. X is by itself. So this is pretty much the strategy for if your denominator has all numbers in it. Sometimes your denominators may have variables, which we'll see later. This is generally the process for if your denominator has all numbers. You have to figure out the least common denominator, and then you multiply that to every term, which will force all of these cancellations to happen. And then afterwards, you will have no more fractions, which is great. Does anyone have any questions before I move on? If not, let's keep going to problem 3 down here. So notice we have, for part 3 here, we have a variable in the denominator as well. So now with our denominator, we have a 2, x, and a 6. So this is one step above now what we had before. Before we had all numbers. So if it were just 2 and 6 as the denominators, our least common denominator would be 6. But now there's an x in the way. And normally, what my philosophy is here, for the least common denominator, is determine the least common denominator part for the numbers and then for the variables. So what would be the least common denominator between, or the least common multiple between 2 and 6? That would be 6. 6 divided by the 2 here. So at least for the numbers, to take care of the numbers, 6 would be perfectly sufficient. Because 6 divided by the 2 here is a whole number, and 6 divided by the 6 here is a whole number. But now what about the x? Now here, we need our LCD to contain an x, so it will handle that x listed out in the denominators. So simply all we do is add an x to compensate for this x here that we have yet to address. So I put an x to take care of that x. So the 6 takes care of the 2 and the 6. The x takes care of the x. It takes a little bit of practice, but slowly all of this, or this process, will make a little bit more sense. So what I'd like to do is just write out everything again. So I'm just rewriting the problem. But now I'm going to multiply every term by the least common denominator. Every term gets its own least common denominator. And remember, even though there's now a variable in the least common denominator, we are looking for an explicit cancellation so we can get rid of these fractions. So here we have 2 and the 6 up here. So 6 divided by 2 would be 3. And so what's everything else that did not get canceled out here? A 1, a 3, and an x. So really that's just left with 3x. So there's a 1 times a 3 times an x. So 1 times 3 times x is just 3x. For the second fraction, the x in the numerator will cancel with the x in the denominator. That's why we put an extra x in the place for the least common denominator. We want that cancellation to happen. And so the x in the numerator cancels out with the x in the denominator. What are we left with? 6 times 6, which is 36. And then finally, for the last one, what will cancel out this 6 in the denominator? Well, the 6 in the numerator. They just cancel, or 6 divided by 6 is 1. So what are we left with? 5 times x, which is just 5x. And notice all the fractions are gone, which is good. All the fractions are gone, which means all we have to do is combine like terms, and we're done. So here we get that 36 is equal to 2x, or that x is equal to 18. Does anyone have any questions about this one so far? For some of you, this might be review. If so, this problem set might not be too bad. Let's look at other ones and make sure we're all on the same page. So let's look at problem 4. And so problem 4, you might notice there's only one denominator. There's only one denominator for problem 4. X minus 1 is the only denominator. That is one concrete denominator. It's not x and then minus 1. It's just x minus 1. So the least common denominator has to be, well, x minus 1. There's really nothing else going on here. There's no collection of denominators that we have to compare together and get a list and find the least common multiple between all of them. It's just denominator, since there's only one, that has to be the least common denominator. There's no competition among the denominators. So I can do what I did last time. Multiply every term by the least common denominator, whether it has a fraction or not. And normally I like to keep these in parentheses if they have more than one term. You'll see why in a bit. But if anything, our choice of LCD will guarantee that once we apply it correctly, we will not have any more fractions in the problem. So in the first fraction, the x minus 1, we're guaranteed that that's going to go away. What makes that go away? Well, obviously the x minus 1 in the numerator. And so what are we left with? Just that x. It didn't get canceled. It didn't go anywhere. Now for the 9 times x minus 1, well, there's no fraction, so there's no cancellation. But notice that I put the parentheses around x minus 1 because we have to distribute the 9. So if you did not put parentheses around the x minus 1, like I did, then you will not know to distribute and you will end up getting the answer wrong. So I put the motivation behind why I did it now as opposed to the other problems is because now my least common denominator had more than one term to it. It had x minus 1. And with this expansion of terms, I need to be considerate about containing all of them together as one concrete value. So that's why I put x minus 1 in parentheses. But there's no cancellation here. It's just 9 times x minus 1. I'll leave it at that for now. And then I see an equal sign. And then for this last fraction, we are guaranteed that the x minus 1 in the denominator will cancel. What does it cancel with? X minus 1 in the numerator. We are left with 1. Not 0, but 1. Left with 1. I see this mistake all the time. You're left with 1. But from here, we can distribute. So I see that 10x is equal to 10, that x would be 1. Or is it? There's one thing we have yet to address here. So we got 1 for x, and you might go into MyMathLab and say, all right, the answer is 1. I'll go ahead and type that in. And MyMathLab is going to say, you are wrong. Why would MyMathLab do that? You just did all this work, and then all of a sudden the answer you just got is incorrect. When we're dealing with fractions, with variables involved, there's domain problems. There's problems with the fact that if you were to plug in 1 for x, notice what you're plugging that into. You're plugging it into, say, a fraction like this. So notice what happens if you plug in 1 for x. You get a 0 in the denominator. You would get 1 divided by 1 minus 1, which is 1 divided by 0. If you try to plug in 1 into this function or this equation, your calculator will say undefined. So that answer we got, we toss it. And we say that there are no solutions. So this is the true answer. And this is the issue we have to worry about whenever we have fractions with variables in them, in the denominator, that is. There's this implicit thing that we have to consider in the back of our minds, which is, all right, I found the value. Will it satisfy the domain? If I plug it in, am I going to end up dividing by 0 somewhere? And in this question, the answer is yes, you will divide by 0. This is exactly why they put this question on the homework, because they wanted you to see this. So you will get a problem almost exactly like this in your homework. And so be aware that if you do all the steps, and then you put the answer as 1 and it's not working, perhaps consider, okay, is it no solutions? I thought I did all the steps right. And it may end up being that way. Does anyone have any questions up to here? If not, we scroll down a little bit. And let's look at number 5. So with number 5, this one's a little tricky because you may notice something interesting with some of the denominators here. X squared minus 4 is not written in a factored form, or in other words, this is a difference of two squares. This is something that comes back from, I guess, the fundamentals of algebra. The difference of two squares tells you that this factors as x plus whatever the square root of the 4 here is, which is 2, then x minus that. And then same thing for this part over here. So you might wonder, what's the point of observing this? Well, now we need to figure out the least common denominator between this factored form and the x plus 2 as well. So all the denominators here, that part I highlighted is one denominator. That is one denominator. And the x plus 2 here is a whole, it's a completely separate denominator. So we have two denominators here. X plus 2 times x minus 2 is 1. And then x plus 2 is 1. And we have to find the least common denominator. So having a factored form is nice because now we can see that there is a repetition between these x plus 2's, which means we don't have to count them twice. You didn't see that before you factored. That's why we factored, so we can see that repetition, and now we can conclude that we can write a factor for every unique thing, for every unique expression we see. So in essence, the LCD, we're going to have an x plus 2 for both that x plus 2 and that x plus 2. And we'll have an x minus 2 for this one here. So now what we have so I'm going to rewrite the problem. I rewrote the problem from before, but I replaced all those denominators with their appropriate factorization. And factoring is nice because when things are multiplied to each other, then cancellation becomes very nice. So now we multiply everything by the least common denominator. So we multiply everything by the least common denominator, which means there will be a considerable amount of cancellation here. We know that the denominator down here will completely cancel. Everything down there cancels with the least common denominator. There's an x plus 2 and an x plus 2. There's an x minus 2 and an x minus 2. They all cancel. And what we're left with is 5x. We have an equal to sign. Next problem, same exact case. X plus 2, x minus 2 cancels with x plus 2, x minus 2. It's the same exact expression. And all we're left with, so notice how much this cleans up. All we're left with is 10. Now finally, for the last one, there's only an x plus 2 in the denominator. So that will only cancel with the x plus 2 in the numerator. So that means we are still left with a -4 times x minus 2. So notice the hardest part of this is applying the least common denominator, but once you do, the problem cleans up really nicely, really fast. And now all that needs to be done, distribute the -4. So we can distribute that. And since I'm running out of room, include that x is 2. We get 9x. Actually, I can put that here. Just go ahead and do that. 9x is equal to 18, and then x is 2. So then, as I mentioned in the previous problem, we have the question of, do we accept this answer? If we apply this answer, will we end up dividing by 0? Some situation. The answer is yes. We do reject this answer. We do end up rejecting this answer because if you try to plug in +2 into, use a different color here. If we plug the 2 into that denominator, x squared minus 4, or equivalently, the rewritten x plus 2x minus 2, then you will get 0 in the denominator. So you get a 0 in the denominator, which means you would reject that answer. And once again, your final answer would be no solutions. So no answer, no solutions. That would be your true conclusion. So the inevitable reality is that I'd imagine a few of you who are trying to just get the homework over with will spam the no solution button in MyMathLab. It may work a few times, but I do recommend you figure out why it is no solution instead of just spamming it. In any case, does anyone have any questions before I move on? Because if not, we're going to look at problem 6, and I anticipate I might need some additional space. So I'm going to do something a little different. So 1 second. Just rewriting the problem. Okay, so we're looking at this problem, and so it's the same idea. We're going to solve for x, and so the first thing I want to do, as we slowly take this a step further, we're slowly adding to what the first step may be. Before we find the least common denominator, we ask ourselves, does the denominator factor at all? Can we factor any of these denominators? If anything, I think the expression on the furthest right should be fairly straightforward. They both have an x in common. So naturally, we can factor out an x. And then the fraction in the middle, same idea. They both have an x in common. So we can factor out an x. Finally, for the one on the far left, that is another situation of a difference of two squares. We had this exact problem before, but there was a 4, and there was a -4 instead of a -1. So instead of using x plus 2 and x minus 2, because 2 was the square root of 4, the square root of 1 is 1. And so that is each denominator. So I'm going to rewrite the problem with this newly factored idea. Off to the side, I'm going to try to determine the least common denominator now. Now we have 3 denominators in general. X plus 1, x minus 1, x times x minus 1, and x times x plus 1. Those are our 3 denominators. And our least common denominator needs to have a component for each component in all the denominators. So I see an x plus 1 and an x plus 1. So naturally, I'm going to throw in one of those for the least common denominator. I see an x minus 1, another x minus 1. Go ahead and throw in an x minus 1. I see an x and an x, so I'll go ahead and throw in an x. I'll put it in the front because it just looks nicer. Really doesn't matter. So our LCD now is x times x plus 1 times x minus 1. And from here, now that we have the least common denominator, we can go ahead and apply it. So now we multiply every term by x, x plus 1, x minus 1. X, x plus 1, x minus 1. And one more time. X, x plus 1, x minus 1. So here, the x plus 1 in the denominator cancels with this x plus 1, x minus 1, x minus 1. We are left with x times x, which is x squared. And then I see that x would cancel with this x. X minus 1 would cancel with this x minus 1. So now we are left with x plus 2 times x plus 1. So I see an equal sign. And so finally, x cancels with x plus 1 cancels with x plus 1. We are left with -2 times x minus 1. Oops. And from here, all the fractions are gone. And so now we just have to apply the final algebraic steps. FOIL over here. Distribute over here. That'd be x squared plus x plus 2x plus 2 is equal to -2x plus 2. I kept the FOILed part in parentheses because we have to further distribute the minus sign. So -x squared minus x minus 2x minus 2. And from here, we combine like terms. X squareds cancel. -x minus 2x is -3x. Minus 2 is equal to -2x plus 2. You can add 3x on both sides. So we get -2 is equal to x plus 2. And then finally, we get that x will be -4. And then finally, we ask ourselves, with the -4, we plug that into any of the denominators, will we get 0? We plug 4, or -4 rather, into any one of these denominators, or any one of these factored additions, then we will not get 0. In fact, the bad numbers for x would be 0, +1, and -1. If we would have gotten any one of those numbers, that would have given us 0 in the denominator. But ultimately, we can conclude that this is indeed our answer, -4. It does not give us a 0 when we plug it into the denominator, so this is our answer. Does anyone have any questions about this before I move on? If not, I'm going to move on. So 6, I just did problem 6 just now. So we'll move on to some of the symbolic stuff. So symbolic meaning there's a bunch of symbols. And there's about 4 of them in your homework. I'll do 2 of them because they get a little tricky. So we'll start off with problem 1. And it's a simple linear equation, and they want us to solve for x. So they want us to get x ultimately by itself. I'll just rewrite it for no reason. So I think you all know what the first step is here, whether or not it may come to you immediately or not. So might I suggest, might I suggest looking at it as if A, B, and C were actual numbers. if I were to write it out this way, then the first step that you would do is add 3 to both sides. Add 3 to both sides. So naturally, over here, we would add b to both sides, because b is just some symbolic placeholder for, say, a number like 3. And so for that right equation, the final step we would do is divide both sides by 4. So we would divide 4 on both sides. So guess what? That's exactly what we would do on the left side here, but 4 is A. And that would be the answer. Also, if this homework assignment, if you saw that it was due on the 9th, I moved that back. So it's not actually due on the 9th. So for problem 2 here. So problem 2, it's a little bit more intricate. We are solving for b, which means we need to figure out a way to get that variable by itself. I immediately see a fraction. So as soon as I see a fraction, the first thing I think of is least common denominator. That's true even if there's a bunch of symbols instead. Now, what's the list of denominators? I see a q, an r, and a b. So in our least common denominator, I need to have some factor for each one of those letters. So naturally, the LCD will be q times r times b. I have q for, of course, the q. I have r for r, and I have b for b. And there's really no other way to say it other than that. And this will make more sense with the ensuing cancellation that will happen. So we multiply every term by the least common denominator, and we should expect cancellations to happen to where we do not have a fraction to worry about. The q's cancel over here. So then we're left with r times b. Well, r times b times 1, which is just r times b. The next one, the r's cancel. And we're just left with q times b. The final one, the b's cancel. And we're left with q times r. Finally, we're trying to get b by itself. But the problem is there's 2 b's in this problem. So we have 2 terms that both have a b in it. But if we have 2 terms that have something in common, naturally we can factor out that common thing. Both of these terms have a b in common, so I'm factoring out a b. And you might wonder, well, why would you do that? And that's because notice I went from having 2 b variables to just 1. I only wrote 1 b on that line, which is good because now we can solve for that 1 b value by simply dividing. B is multiplying this R plus Q. So naturally, we can divide it. I get exactly that B is QR divided by R plus Q. So this is a tricky problem. I've been asked many questions about this in the past from students. It's definitely why I wanted to talk about it and want you all to make sure you can follow along with it. Let's see if you can recreate these steps on the homework. Does anyone have any questions about this before we move on? So finally, we're going to look at, well, we do have these two application problems. So we have these application problems. Something about a college bookstore marks up the price by 25%. They give us the original selling price, and they want us to know how much did the bookstore pay for the book. So what's happening here? So let's try to think about this. There's a publisher that gives a book to the bookstore. Bookstore buys the book, and then they mark up the price of the book so they can make a profit. If they went and bought the book and then sold it at the same value, then obviously they're not making a dime off of that. They want to make some money. They want to mark it up. So pretty much by the time you're seeing the book in the bookstore, so by the time you see the book in the bookstore, the final price is $63. The question is, what was the original price? As in, what was the price that the publisher sold it to the bookstore before the bookstore went ahead and upped the price by 25%? So we're going to turn this into an algebra problem. Because naturally, with question marks in algebra, what that really means is X. So what the bookstore did, they purchased the book at the original price, then they marked it up by 25% to get the new price of $63. So algebraically, what does it mean to find 25% of something? This is when you move the decimal place over. So here, now what it is, original price, add 25% markup, and that's where the $63 comes into play. So really, all we have is x plus 0.25x is equal to 63, and now it's an algebra problem. X plus 0.25x, those are like terms. That is now 1.25x, because that's 1 plus 0.25. So then we have 63 divided by 1.25. $50.40. That was the original price. So that was the original price that the publisher received, or that was the original price that the bookstore paid for the book from the publisher. And then for the bookstore to make some money, they marked up the price by 25%. And so 25% of $50.40, marking that up by the 25%, that is $63. So they made a profit of a little under $13 for the book. Does anyone have any questions about this one? If not, let's go ahead and look at example 4 as well. All right, we have something about a rectangular window. So I'll naturally start drawing a rectangle. We know that the perimeter is 40 feet. The perimeter is if you add the lengths of all the sides together. The width is 6 feet more than the length. 6 more than the length. That means that there is a length value. And they want us to determine the dimensions of the window. So naturally, here's all the sides for the rectangle. We know that the width is 6 more than the length, and the length is something. We don't know. So the perimeter is when you add all the sides together. So the perimeter would be if you added the length and the length again, and the width again, in general. But we know that the perimeter is 40. And we know that the width is 6 plus L. And the reason why is now we just reduced it by one variable. Now instead of having L's and W's floating around, we just have L's, which makes this one variable. So I count 4 L's, so I'll put 4L. I see a 6 plus another 6, which is 12. And then finally, I subtract, well, I solve for L. It's a variable problem. So that will be 28 equal to 4L. So what is that, 7? So that's the length. The width is 6 more than the length, which is going to be 13. So the dimensions are that the length is 7 and the width is 13. So that's 2 types of word problems you can expect on this homework. If everyone's okay with that, I'm going to move on to inequalities in interval notation. So in the previous chapter, we talked about interval notation already. We're going to talk about it a little bit more here and show how inequalities and interval notation are both helpful. The reason why inequalities are helpful is because we can do algebra with them. Inequalities can have variables involved. So that means for, say, a problem like number 1, we can move things around, we can multiply, divide, combine like terms, and all of that. You cannot do that with interval notation. So interval notation is a more compact final answer, and inequality form is better with algebra. So for a problem like this, for number 1, I see a fraction. So I instantly think least common denominator. There's only one denominator, which means it has to be the least common denominator. I only see one denominator, which is 5. So that has to be the least common denominator. I multiply every term by 5. And yes, the 1/5 times x minus 8, that is one term. That is one term. So I don't have to multiply numerous 5s. That's just one 5. Naturally, the 5s cancel. And we're left with x minus 8 is less than. I see an x times 5, which is a 5x. And I see a 16 times 5, which is 80. And so now that we applied the least common denominator, all the fractions are gone. And we can go ahead and start combining like terms. And so we get that x is greater than 22. Well, negative 22. And so this answer, you're going to notice it's going to ask for both set notation and interval notation. This first answer we found is set notation. That is set notation. If they ask you for set notation, they want a solved inequality. They want the x by itself. In interval notation, this is what we talked about before. So that would be negative 22 to positive infinity. Of course, that would be interval notation, because x is greater than negative 22. So greater as in it goes to positive infinity. Does anyone have any questions about this? If not, we'll look at problem 2, which is a compound inequality. Compound in the sense that there's inequality symbols on both sides. So that means if you were to solve for x, means say add 6 to both sides, well, really you're adding 6 to all the sides, because this is a compound inequality. So now it's 6 less than or equal to now 2x less than or equal to 10. And then dividing by 2, 3 less than or equal to x less than or equal to 5. So inequalities, whether they be regular inequalities or compound inequalities, are good for algebra. And now we have the inequality solved, which means x is by itself. So this would be the set builder notation. And equivalently, this would be the interval notation. They may ask for one or the other or both. If nobody has any questions about this, I'll go ahead and keep that on the screen while I talk about real briefly reciprocal properties. There's maybe 2 or 3 problems at the very end which do deal with inequalities, and there's a few situations you have to consider here. They simplify very nicely. They just start off looking fairly horrendous. If you have one of these negative exponents greater than 0, or greater than 0, then all it says is you're allowed to get rid of the exponent. We'll see this below, but if you have a -1 exponent less than 0, well, guess what? Same idea. You could just get rid of the exponent. So 3 or 4 cases work that way. The bottom case is a little bit different, because naturally, if you square something, then it's hard to be less than 0. Because when you square something, naturally, that thing is positive. That is why 3 of these 4 cases, all it says is you can get rid of the exponent. That's it. Boom. Just exponent gone. And that final case, it means if you can remember it, then your answer, you can just state it immediately. So with example 6, and we'll talk about the domain thing in a second, but with example 6, we look and see which one of the above criteria does this match. I see a -1 exponent less than 0. So it matches this form, which means that we are simply allowed to just get rid of the exponent. So that's it. That's how we interpret it. And we can solve for x now that that pesky exponent is gone. So it starts off a little bit case-by-case oriented, but after that, we can solve for x. And they want the answer in interval notation. We have it in set builder notation. Last problem in the section is find the domain of this square root. We actually did this in the past chapter. This is one of the criteria that we talked about. Domain of the square root. It says you can toss the square root symbol. So that means if you have the square root of 6x minus 12, it says you're allowed to just toss the square root symbol, provided you set everything underneath greater than or equal to 0. And then we can solve for x. So that is the final answer here, and that concludes the problem set for this section. So I guess before we wrap up, so I am out of time. So as a reminder, the assessment, you have until Friday at 6 p.m. to take it. 60 minutes, 13 questions. You take it on your own. Please take it in a reliable place, because if you have any technology issues, there might not be much I can help you with. So please make sure you take it in a good spot that it will hold out for 60 minutes. You don't have to turn in any scratch work to me or anything. And I'll send out an email after I'm done teaching for today, specify everything else. Workbooks Friday, the 2 homework assignments are homework and quizzes due tonight. And I'll answer any emails I get before 8 p.m. If you have any questions, I'll stick around. Other than that, have a good day. One second.